Welcome to Homework Lib.
To start out, this problem gives us the following situation. We have a hydrogen molecule with a moment of inertia of 4.6 times 10 to the minus 48 kilogram meters squared, and it is rotating around. The problem wants us to find out the temperature at which the average kinetic energy of this molecule is equal to the energy separation between the L equals 0 rotational band and the L equals 1 energy level. So, to get started on that, we are given that the energy of a free ideal gas, which we'll call E average, is simply 3 over 2 multiplied by Boltzmann's constant and the temperature. And the other thing we're going to need is the energy of a molecule with some rotational quantum number L, which is L times L plus 1 times the reduced Planck's constant squared all over 2 times the moment of inertia. Now, in this problem, the moment of inertia is given, so we have that. And you can see right away that the L equals 0 rotational band just goes away because there's no rotational energy there. But at the L equals 1 level, so if we want the difference, it's E1 minus E0, which is just E1. So we get 2 times h bar squared over 2 times I, leaving just h bar squared over the moment of inertia. And by plugging that in, you get to two significant figures, 15 millielectron volts. That's little m eV. And now we want to do a simple equivalency where we set these two things equal to each other. And so we take that delta E, set it equal to 3/2 Boltzmann's constant times T, get that the temperature is going to be 2 times the change in energy over 3 times Boltzmann's constant. And plugging in this, we get that the temperature is quite chilly, 116 Kelvin, or 120 if we want to go to two significant figures here. And that's not the end of what the problem is asking, however, because it wants us to tell what does this value for that transition tell you about the number of hydrogen molecules in the L equals 1 level at room temperature. And the way to think about this is if you give this hydrogen molecule some outside energy, if you give it at least 120 Kelvin, you're likely to incite this L equals 1 phase transition. So you can assume that at any temperature higher than this, you're going to have a substantial number of hydrogen molecules in that L equals 1 level. And thus, if room temperature is 300 Kelvin or so, then obviously you're going to have quite a few excited hydrogen molecules.